Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, I'm going to work on some of my notes that I provided to my students for operations of functions in our unit on functions. So basically, what we're going to look into is applying the operations such as addition, subtraction, multiplication, and division, learning how to simplify. But we're also really the main two things is not only applying the operation, but being able to identify the domain as well as how to evaluate those compositions and composition. So what I did is I kind of started off with a nice little warm-up with my students, just kind of help them evaluate. And I wanted students, just kind of remember when you have a function like, when you have evaluate, what exactly we're doing is we're just replacing the input value with whatever's, we're trying to input for. So in this case, wherever input value, instead of x of our function, it's going to be as 1. So I'm just going to replace 1. And I kind of use this time to go with my students to make sure that they understood the use of parentheses. Because even though most students could probably do this problem in their head, I wanted them to get used to using parentheses, which we'll see coming up. Next thing is 0. Hopefully you recognize that is going to be the y-intercept. So that would be 0, that would be 0. So without showing much work, I can just plug that in as 1. This -2 is really important, though, to use parentheses, because if you don't use parentheses, then it's going to look like this, -2 squared, which a lot of people might just write as -4 squared. But -2 squared is actually equal to a positive 4. -2 times 2 is equal to another positive 4 plus 1, so that's equal to 9. And here's maybe another better example of this -x. So -x squared in parentheses minus 2 times -x plus 1. So again, -x squared is -x times -x, so that's a positive x squared. This becomes a positive 2x plus 1. And then again, so now we kind of worked on some variables and just like a -x. Well, if I get a t, again, the idea is just to follow the formula. So f of t is just going to be t squared minus 2t plus 1, right? Even if I did 3t, you're just going to plug in this 3t squared minus 2 times 3t plus 1. Now you could simplify this one. 3t squared is 9t squared minus 6t plus 1. And then really this expression is, again, if you've kind of followed this rule, you're just going to do the exact same thing here with this expression. So now I'm going to do x plus h squared minus 2 times x plus h plus 1. But I went to my students, I said, please make sure we understand that x plus h squared is equal to x plus h times x plus h. It is not equal to x squared plus h squared, which is like one of those common mistakes a lot of students that you'll see. So I wanted to make sure I did that, and then I just kind of worked it out in my head because next chapter we'll spend a lot more time working out multiplying binomials. Then I just distribute here, so that's a -2x minus 2h plus 1. And this next one was kind of confusing because we had g of x. But again, it's a function. We don't know what the function is. But again, if you just follow what we did for like t, just plug it in. So this is g of x squared minus 2 times g of x plus 1. Okay. Then we kind of went into the operations of functions, using this notation that hopefully was a little familiar with them. However, the main thing I wanted to get with the students was understanding that the domain of addition, subtraction, and multiplication of two functions is the intersection of the domains, whereas the domain of the quotient, which I meant to actually change this, is going to be the intersection of the domains plus the restriction of g of x in the denominator. So the restriction of the denominator of the function being in the denominator. So it does not change it once it gets simplified, but I wanted to actually change that sentence right there, which I'll do later. All right, so we're going to apply some operate. So what we did is we applied operations. So I gave the students, basically these operations, and we're going to work through kind of multiple different examples going on through there. So we have 8 different functions, and then I just kind of put them in groups and said, all right, let's go ahead and add, subtract, simplify, practice simplifying, and then determine the domain and evaluate for x is equal to -1. So evaluate, meaning just like we did, in our warm-up. Find the value. But now you're not just finding the value of one function, you're finding the value of an operation. So we have f of x plus g of x. Using the notation, we know that is f of x plus g of x. So now I just got to remember what is, f of x. Well, f of x is x minus 3 plus g of x, which is 2x, let's see, plus 4. I rewrote them down so I'd remember them. And then in this case, we are just going to combine like terms. So that's going to be a 3x plus 1. Now, what did I say? Did I say to find the domain? Yeah, I did. Okay, so we're going to find the domain of this. Now, the nice thing is, when we're doing these problems, before I even do the domain, I kind of want to find the domain of f of x as well as in g of x. And f of x and g of x both have a domain of all real numbers. So again, the intersection here of all real numbers and all real numbers is just going to be all real numbers, right? And then we want to evaluate, so that's going to be f plus g of negative 1. So now I'm just going to plug in negative 1 in for x. So you could plug it into the original function, or you can plug it into the simplified function. Since I was able to do this math here rather quickly, I'll do that. So negative 3 plus 1, which equals a negative 2. All right, the next one I did h plus j. So h of x is square root, first of all, that's h of x plus j of x. All right, so therefore we have h of x, which is square root of x plus 3, plus j of x, which is 1 minus x. Now, obviously, these are not like terms. They don't have the same radicand as well as index, so therefore we can't combine them. We can determine the domain, though, of each one. So the domain of this function is, it's going to be all numbers greater than or equal to negative 3. And this function is going to be all numbers less than 1. Yes, 1. So if you're kind of wondering where I came up with those, again, what we talked about in class was whenever you have a radicand, set it greater than or equal to 0 and go ahead and solve. So x is greater than or equal to negative 3. And here I have 1 minus x is greater than or equal to 0. Add the x, so therefore x has to be less than or equal to positive 1. So that's where those domains came from. But again, now we're looking for the intersection, right? So to understand this, I'm actually going to do a number line here. So let's say negative 3. And here's 1. So this is all numbers that are greater than or equal to negative 3, and all numbers greater than or equal, or less than or equal, than 1. So you can see the only values, the intersection of these two domains is going to be from negative 3 to 1. All right, and now just to go ahead and evaluate, I'm going to plug in, let's see, what am I plugging? I'm plugging negative 1, right? Okay, so I'm going to write this notation, h plus j negative 1 is equal to the square root of negative 1 plus 3 plus 1, square root 1 minus negative 1. Negative 1 plus 3 is going to be 2 plus 2. And now you can see that they both have the same index as well as the same radicand, so I can combine these to give me 2 square root of 2. All right, let's go on to another addition and subtraction here. I had k minus l, so that one was, so again, that's equal to k of x minus l of x. So k of x was 1 over x minus 2, and l of x is 3 over 2x. 3 over 2x. Okay, so just remember when you're adding or subtracting rational functions, you got to have a common denominator. So what we did is to find the common denominator. In this case, typically we want the easy way just to identify this is just to multiply the two denominators to give you a common denominator. We'll spend more time in chapter 3 looking for ways to do this a little bit easier. But I just kind of told students, let's just kind of get through this. We got to make sure fractions got to have common denominator. An easy way to get a common denominator is just to multiply the denominators. So therefore, I'm going to multiply by x minus 2 over x minus 2, unless you see it's obvious that they have a common, a term in common. So in this case, I have 2x over 2x times x minus 2 minus 3 times x minus 2 over 2x times x minus 2. Now you can see that the denominators are exactly the same. I can go ahead and distribute this, and then I can just combine the numerator here together. So That's going to give me 2x minus 3x plus 6 all over 2x times x minus 2. And then therefore that will give me a final answer here of let's see, that's going to be a negative x plus 6 all over 2x times x minus 2. Okay, now again, let's look at the domains. So the domain of k of x, which is my first function, is basically all real numbers except for 2. The domain of L of x is all real numbers except for 0. So if you think about this, if we combine these two, right, we basically have a number line, which is all real numbers except for 2, and all real numbers except for 0. So these are the only undefined values. Everything else is good. So my domain here is going to be from negative infinity to 0, union 0 to 2, union 2 to infinity. If I want to plug in negative 1, you could plug it into your original example up here, or you can just plug it into the simplified answer, which I'm going to do. So this was k minus L. So let's do k minus L times x is equal to negative 1 plus 6 all over 2 times negative 1 times, negative 1 minus 2. All right, so minus a negative 1 is a positive 1, so that's equal to a 7. And therefore, that's a negative 2. Let's see, negative 1 minus 2 is a negative 3 times a negative 2. So negative 3 times a negative 2 is a positive 6. Oh, that's a positive. That's a positive 7. Aha, I knew it. Come on, there you go. Okay, so that subtracts, that gives you a positive 1, that's 7, and then therefore, okay, perfect. All right, then we have an m and an n. So m and n, so that's basically m of x plus n of x. And m of x in this example was x squared minus 3 plus n of x, which is x squared minus 3x plus 2. All right, now again, nice thing, guys, just combine like terms. For exponents, remember, they have to have the same exponent or base as well as power. So that's a 2x squared minus 3x minus 1. The nice thing here is my domain is all real numbers for this one and all real numbers for that one. So therefore, by adding and subtracting them, you know, the combination of two domains with all real numbers here is just going to be all real numbers. Now go ahead and evaluate this. So I'll do m plus n. It's probably easier to plug in the negative 1 here. That turns into a positive 1, so that's 2 plus 3 minus 1, which is 4. Okay. All right, last two here. Now let's get into two more subtractions. So I have g minus m. So let's see here. That's going to be g of x minus m of x. G of x is 2x plus 4. So that's a 2x plus 4 minus m of x, which is a x squared minus 3. Now, the reason why I wanted to include this is we're subtracting polynomials. Make sure you don't write it just like this. Make sure you include your parentheses. So when you actually subtract them, you got to make sure you're subtracting both terms, the x squared and the negative 3. So it's actually going to look like this. Okay, now we can rearrange this to give us a negative x squared plus 2x and then plus 7. Okay, again, we notice that the domain of g of x is all real numbers. The domain of m of x is all real numbers. So if we're subtracting two functions and all their domains is all real numbers, then we're going to have all real numbers. And then last but not least, guys, is f of x for addition and subtraction. So we have f of x minus k of x. All right, f of x was x minus 3 minus k of x, which is 1 over x minus 2. Okay, what I told students here is, again, if you're trying to simplify or subtract an expression minus a fraction or a rational expression, you got to write them as expressions here. The common denominator of 1 and x minus 2 is x minus 2. So therefore, I'm going to multiply by an x minus 2 on the top and the bottom. Hopefully you recognize we can multiply this out. So I'll just write it out there. So therefore, this is x minus 2 times x minus 3 all over x minus 2 minus 1 over x minus 2. Now, I'm just going to multiply that out in my head here. So that's going to be x squared minus 5x plus 6 all over x minus 2. And there, so that's minus 1, right? Because you can subtract them now with as far as the common denominators. So my final answer is x squared minus 5x plus 5 all over x minus 2. The domain here is we got to do a combination of the domain of x minus 3, which is all real numbers, and the domain of x minus 2, which is all real numbers except for 2. So again, if you look at this from like a graphical perspective, we have all real numbers, and then we have all real numbers except for 2. So the only domain where both of those domains is true is going to be all real numbers except for 2. Again, we're finding the intersection where both of the domains have to be true. And then if I wanted to evaluate for 1 here, kind of run out of space, I can just do f minus k of negative 1. And then let's just, crap. Let's do it over here. Let's move that up. Okay, so if I wanted to evaluate this, I'll do f minus k of negative 1. That's going to give me a negative 1 squared minus 5 times negative 1 plus 5 all over negative 1 minus 2. Let's see, that's a 1 plus 5 all over negative 1 minus 2. So you owe me $1, you borrow 2 more. That's going to be a negative 3. So that's going to be a negative 11/3 because you take the negative in the denominator and just put it in front. All right, so basically what I want to do, the whole purpose of doing that, all the groups are doing those problems, was just to basically open up a discussion as far as how the domain changes, or actually how it doesn't change, if we're doing addition or subtraction, as well as the functions change when we're doing subtraction. But again, the order doesn't matter when we're finding the domain, we're just finding the intersection. So then we went into multiplication, and then I asked students to go ahead and evaluate for x is equal to 0. So let's go and do some multiplication problems. So we have f of x times g of x. So that's f of x times g of x. So let's see, f of x is x minus 3. G of x is 2x plus 4. So just remember the distributive property, or FOIL, as some people might use. That gives us a 2x squared plus 4x minus 6x minus 12. Your middle terms you can go ahead and combine. Okay. Again, notice that the domain is going to be the intersection of my two domains, which is all real numbers and all real numbers. So therefore, my domain here is going to be from negative infinity to infinity. And then if I want to evaluate from f of g of 0, let's just plug it into the end. And I like this final form because if I plug in a 0, that's 0. If I plug in a 0 here, that's 0. So therefore, I'm just going to have a negative 12. All right, let's go with division. When I talked about division, I told students not to have to simplify. We're not going to be doing anything that they remember from Algebra 2 at this point. We're just going to be writing it as the quotient and stopping right there. So this is a and g of x. Okay. Now, it's important to understand these two domains. The domain here was all real numbers. From all real numbers that are larger than or greater than or equal to negative 3. And the domain of this function in the denominator was from negative infinity to 1. But what I said in the notes section was it's still the domain of the function in the numerator, function dot, still that intersection, plus the new restriction that the denominator cannot equal 0. So then we got to say, well, what denominator, what value makes my denominator equal to 0? Well, that is 1. So the domain of this function is going to be the intersection of, basically it's going to be -3 to infinity with the intersection of -infinity 1. So not including 1 though, because that is in the denominator. So basically when we go ahead and graph this, we say, all right, here's -3 to infinity, right? And now we have 1, which is an open circle. And again, so what we're looking for, what is the domain for both equations to be true? And that is going to be, the final answer is from -3 to 1, open circle. All right, so really kind of important to understand that even though you're looking at your intersection of these two domains, you also have to take into consideration you're putting a function into the denominator, so therefore you're going to have a new domain there. And then we need to evaluate, evaluate for 0. So h of j of 0, basically we have 0 plus 3 divided by 1 minus 0. Well, 1 minus 0 is 1, square root of 1 is 1. So that just leaves me with the square root of 3. All right, next one is k times L. So k of x is 1 over, so that's k of x times L of x. So that's k of x times L of x, which is 3 over 2x. Just remember when you're multiplying fractions or rational expressions, you're multiplying straight across. So that's going to be 1 times 3, and then x minus 2 times 2x. Now, you don't need to simplify this, or I didn't ask my students to go ahead and simplify this. I said you can just leave it, as your denominator like this. That's perfectly fine for me. And that tells us now our domain. Again, it's the intersection, but basically you can see the simplified result. We hopefully understand that the denominator cannot equal 0, and the denominator cannot equal 2. So again, going back to our previous problem, the denominator cannot equal 0, the denominator cannot equal 2. Everything else, though, is good to go. So we'd write our domain here from -infinity to 0, union 0 to 2, union 2 to infinity. Go ahead and plug it in 0. I can actually, don't need to show my work here. You can show your work if you want to. But we can see that from our domain, 0 is not defined in the function, right? Because if you plug in 0, that's going to make that function undefined, right? That's going to make the denominator 0. If you plug 0 into this function, you're going to get 0 in the denominator. So I'm not even going to show the work. I'm just going to say it's undefined. I can see it from this answer, in my head, as well as seeing it in the domain. Let's go over to a division problem. So we have m x squared minus 3 all over x squared minus 3x plus 2. Plus 2, sorry. All right, so that's x squared minus 3x, and from there, nothing else we can really do at this point. We're not going to do any division, long division, synthetic division. So therefore, we do need to figure out what the domain is. So therefore, what we learned in class was you can set the denominator equal to 0, right? Because we haven't solved this yet. So that's the interesting thing about the division, right? Previously, we're taking something that's all real numbers and all real numbers. But once we put that function in the denominator, we have to satisfy now this restriction that the denominator cannot equal 0. So even though both functions were all real numbers, once you do a quotient or once you put that function in the denominator, we have to satisfy this. We have to satisfy that the denominator cannot equal 0. So then I go ahead and factor this to x minus 2 times x minus 1. And therefore I can say x minus 2 is equal to 0 and x minus 1 is equal to 0. So therefore x is equal to 2 and x is equal to 1. So therefore my domain is all real numbers except for 1 and 2. So it's -infinity to 1, union 1 to 2, union 2 to infinity. All right, what was I going to say? Oh, we got to evaluate. And the nice thing is if we evaluate, kind of notice, this is kind of an interesting thing here, m over n of 0. If I plug 0 into the numerator, that goes to 0, so I'm left with -3. If I plug a 0 over here, that goes to 0, that goes to 0, so I'm just left with 2. So I'm just left with a -3 over 2, right? I can kind of simplify a lot of my work. I don't need to show everything by plugging it in. Next one is j and k. So again, that's j of x times k of x. If I didn't write that last time, Yeah, I should probably write that. M of x over n of x. Just remember that notation because I know some students still get it kind of a little mixed up. All right, so j of x here is 1 minus x. And k of x is 1 over x minus 2. So this one's kind of an interesting one. Obviously, j of x, we already talked about the domain, which is negative infinity to 1. And k of x, we already talked about the domain, is negative infinity to 2, union 2 to infinity. But remember, when you're multiplying an expression times fraction, again, or just multiplying fractions, you multiply numerator times numerator, denominator times denominator. So the interesting thing that happens here is we're left with a 1 minus x over an x minus 2. Now, we already had the restriction of 2 could not be in the denominator, or 2 could not be in the domain, and by multiplying them, that did not change. I didn't add any new restrictions with my denominators. Nor did I add any restrictions with my radicals, right? We're just really actually just finding the combination of these. Now, again, it's the intersection though. So when we're combining these, we got to combine the two domains. So we have one domain from 1 less than 0, and then we have all real numbers except for 2. So again, what we're looking for is where are the two domains intersect? What is true for only both of those domains? Well, that's only going to be from 1 to negative infinity. Sorry, negative infinity to 1. Okay, because anything over here, only the one function is defined. Go ahead and plug in 0. So j of k of 0 here. Let's see here. We're going to have square root of 1 minus 0 all over 0 minus 2. So 1 minus 0 is 1, so we have 1 over negative 2, which again you could rewrite as negative 1/2 and so on and so forth. Another division problem here, we have n of x over h of x. So this example, I have x squared minus 3x plus 2 all over h of x, which is x plus 3. Okay, so again, we already have the restriction. I gotta be careful. N of x over h of x. Okay, so we already know the domain, n of x, the domain of n of x is all real numbers, right? It's a quadratic. The domain of h of x, so this one's all real numbers. And the domain of my denominator here is all real numbers larger than negative 3. However, once I put this in the denominator, negative 3 cannot be defined because negative 3 makes the denominator equal to 0. So I have something that's all real numbers and then negative 3 equals 0. So my domain here is going to be negative 3, comma, infinity. And then if I wanted to evaluate for n of h of 0, I notice that my numerator is just going to be 2 over the square root of 3. And I'm just going to leave that as is for right now. We could rationalize the denominator if you remember it, but that's not my big purpose here. All right, so the main thing I want students to come away with this is obviously, again, how multiplication does not impact the domain, but when we're dividing, when you put a function in the denominator, that really changes everything. You have to make sure you satisfy that restriction of a function being in the denominator where it cannot equal 0. All right, and then really the main stage that we wanted to get into this one was the composition, making sure you understand the fog and the goff, basically this plugging in one function into the other, which we did at the beginning, right? So I introduced this kind of at the beginning with the warm-up, so therefore this notation is not something crazy. The important thing though about composition is when we're finding the domain, it's the intersection of the domain of the input function, the function you're plugging into the other function, as well as the composition of the two functions. So we'll go ahead and I'll make a little bit more sense as we kind of work through that. Then I ask the students to go ahead and figure out the composition, determine the domain, and then evaluate for x equals 1. All right, so I'm going to rewrite this because I know a lot of students do not like this notation, so this is where they usually get mixed up. They don't know what you're plugging into what. So g compose f of x basically means g of f of x. So that means I'm basically just going to plug the f of x function, into the g of x function. So, for instance, the first one I'll just kind of work out very slowly. So g of x is equal to 2 times x plus 4. So if I do g of f of x, then I'm going to do 2 times f of x plus 4. And then we say, well, what is f of x? Well, f of x is x minus 3, right? F of x is equal to x minus 3. So therefore, you're going to do 2 times x minus 3 plus 4. You can apply some distributive property. Plus 4, combine like terms, 2x minus 2. So that's kind of the, the long form of that, so you can see some work. I'm not going to show as much steps from there, but hopefully you can kind of see what's going on. The other thing I want you to kind of recognize is, again, the domain. So we have f of x is your input. So that's the input. And then once you plug one function into the other, right, this is the composition. Now, when we're talking about the composition, we're really talking about the composition from it not being simplified, but you can even simplified, but you're looking for the intersection of the domain from the input function as well as the composition, like once you've plugged in that value. So actually, let's do it from here. And you'll see what we'll have is, there's your input, right? So it's the function of the input, the function you're plugging in, and the composition. Well, the domain of x minus 3 is all real numbers. The domain of 2x plus 4 is all real numbers. So therefore, the domain of my composition here is going to be all real numbers. And I'm just using r and the interval notation kind of interchangeably here. And then I can compose for evaluate. And since I've already simplified this, that's going to be easier to evaluate for what? 1? For 1, yeah. All right, so therefore I'll plug in 1. So that's a 2 times 1 minus 2, which is equal to 0. Next one is h of g of x. So that's going to be h of g of x. All right, so h of x is going to be square root of, let's see, g of x, which is 2x plus 4. So I'm just going to use parentheses, so therefore you can see what I'm plugging one into the other. Okay, so this is h of x, and then that is your little g of x, right? So I'm just kind of showing a little bit of work because I'm not going to show this for each and every one. So there's my g of x, and then that's your h of x, because h of x is x plus 3, and you're replacing the x with g of x, or 2x plus 4. Therefore, then this becomes 2x plus 7. Okay, so again, we have a domain that's all real numbers, right, which is 2x plus 4. But then we have to now intersect that with this new domain, which is 2x plus 7. And again, remember when you have a radical and you need to set the domain, you set it greater than or equal to 0. So therefore, I have 2x is greater than or equal to a negative 7, and then divide by 2. And I have x is going to be greater than or equal to a negative 7 halves. So the domain in that case is going to be negative 7 halves to infinity. To go ahead and evaluate this for 1, I'm just going to plug a 1 in here. 2 plus 1 is 2. 2 plus, all right, let's just write it out there. 2 times 1 plus 7. 2 times 1 is 2, plus 7 is 9, which is equal to 3. All right, let's do some more. K of n of x. So this is basically k of n of x. All right, so k of x is 1 over x minus 2. So k, oops, you know what? I should probably write that in a better notation. Yeah, I wrote that wrong. So yeah, let's just do it. That is equal to that. Okay. All right, so that is equal, oops, shoot, come on. No. Okay. There you go. All right, k of n of x. So k of x, let's see, k of x is going to, so that's going to be equal to 1 over parentheses minus 2, right? Because k of x is x minus 2. And then I'm just going to plug in n of x, which is x squared minus 3x plus 2. Well, when I go and get rid of my parentheses, because I don't really need parentheses here, I end up with a simplified version of 1 over x squared minus 3x, right? Because positive 2 and negative 2, they add to 0. So now it's my new domain. So again, my input value, my input function is all real numbers. However, my composition now, like this answer, is going to be all real numbers except for the values that make my denominator equal to 0. So I'm going to have to factor this a little bit. I can factor out an x. And then hopefully you see that my domain is all real numbers except for 0 and 3. So domain is everything except for those two values. So that intersected with all real numbers is going to be from negative infinity to 0, union 0 to 3, union 3 to infinity. You'll look close there. All right, and let's go ahead and evaluate for f of 1. We can just plug that in for right there. So I'll just do k of n of 1, and it's going to be 1 over 1 times 1 minus 3, which is 1 over 1. Let's see, that's negative 2. So that's a negative 1/2. All right, then we have f of L. F of x is x minus 3. So that, well, anyways, let's do that's f of L of x. Okay, so you're going to plug the L of x function into the f of x function. So f of x is x minus 3, but we're going to plug in the L of x function, which is 3 divided by 2x. Okay, so without parentheses, that's 3 over 2x minus 3. Well, again, we got to subtract them. We got to make sure they're numerators here. Get common denominators. So I'm going to multiply by a 2x over a 2x. So this gives me a 3 over 2x minus 6x. There's really nothing else I can do here. Again, my input value, the 3 over 2x, this Lx, has a domain of all real numbers except for 0. And once I plug it in, that domain has not changed, right? It's still all real numbers except for 0. So that's negative infinity to 0, union 0 to infinity. And then if I want to evaluate for 1, three minus 6 times 1 over 2 times 1. So 3 minus 6 is going to be negative 3 divided by 2, so that's a negative 3 halves. Whew. All right, 2 more on compositions. The next one is going to be L of j of x. So that means L of j of x. So you're going to plug the j of x function into the L of x function. So the L of x function is 3 over 2x. Right? But instead of x, we're going to leave that as an open variable because that's what we're going to plug in j of x in for, which is the square root of 1 minus x. Nice. Okay, so again, my domain here of my input is from negative infinity to negative 1. However, now that it's in the denominator, it can't be equal to negative 1 because that makes the denominator 0. So my domain is unchanged. It's just now I have to make sure I apply this restriction of it being in the denominator because the composition has it in the denominator, right? And then I can evaluate for 1, which is just plugging in a 1. However, you can see that when you plug in a 1, again, that's undefined. So that is not going to be that is going to make the denominator 0, so therefore it's undefined. And the last one is just plugging one function into the next, really. Like you're plugging the function into itself. So you're doing m of x. So, basically this is m of x squared minus 3. Or sorry, x squared minus 3, but now you're going to replace that with m of x, right? You're plugging in m of x into m of x. So that's really, x squared minus 3 squared minus 3. And again, remember, you can't distribute the x squared. You got to multiply it by itself. I'm just going to write this out just because I want students to see this. Hopefully you recognize that's a perfect square trinomial, maybe. X to the 4th minus 6x squared plus 9 minus 3, which gives you x squared minus 6x squared plus 6. Okay, the other important thing to kind of take note with this is that The domain of the input is all real numbers. The domain of the composition is all real numbers. So this domain is all real numbers. And then if I want to evaluate for m, mom, of 1, then I'm just going to plug in a 1. So we'll just have a, oops, that's supposed to be a 4th. So 1 to the 4th, which is 1, minus 6 times 1 squared, plus 6. So that's 1 minus 6 plus 6, which is just equal to 1. Very good. All right, ladies and gentlemen, on to the last and final stretch here, which is even and odd function. So we've already talked about even and odd function in my class, so I didn't kind of go over this much. The only thing I really kind of spent time with them is understanding this new notation and then kind of making sense of that. And the way that I make sense of it is, here's our most famous even function, or at least the one we're most familiar with, I would say, which is x squared, right? Y equals x squared. It's symmetrical about the y-axis. So if here's x, like x covers right here, that's fx. Well, again, the thing about being symmetrical is, they're both going to have fx. So that means, f of x is equal to f of negative x, right? They both have the same value. That's a even function. Whereas odd functions are symmetrical about the origin, right? So our famous odd function here is, x cubed. Because obviously, when we have here, that's equal to f of x. But negative x is not equal to f of x. Negative f of x is equal to a negative f of x. So that's why that makes sense. If you plug in negative x and you get the opposite, then therefore you're going to get you're going to have an odd function. So what I did with the students is we just kind of worked through these examples. Basically, you're going to do the same test. If you plug in, basically what we're going to do is we're going to plug in negative x, which again was from our warm-up. If you plug in negative x and you get back the original function, then it's even. If you plug back negative x and you get the opposite of the function, it's odd. And if you plug in negative x and you get neither the negative or the original function, then it is neither. All right, so let's go ahead and plug some values in. So in this case, I'm just going to plug in f of negative x. So I get 3 times negative x to the 4th. Minus 5. The one thing I kind of remind students, whenever you have a negative value or number or variable raised to an even power, it's always going to be positive. So this is 3x to the 4th minus 5, which you guys can see is exactly back to my original function. So therefore that is even. The next one, do the same thing. Check g of negative x. So I get 8 times negative x minus 2 times negative x. Well, 8 times, negative x cubed. So negative x cubed is negative x times negative x times negative x, which gives you a negative x cubed. So I'll do this one time. I'm not going to write this out every single time, though. But you can see that goes to negative x cubed, and that's a positive 2x. So a negative x cubed times a positive 8 is a negative 8x cubed plus 2x. Now, a lot of students don't recognize that this is the opposite of our original function, right? That's positive, that's negative, that's positive. But another easy way to do that is just factor out your negative. Okay? Now you can see it's the opposite of my original function, so therefore this one is odd. All right, next we have g of x, another g of x, I guess. So let's go ahead and plug in this negative. So we have a 2 times negative x cubed minus 3 negative x squared plus negative x minus 2. All right, so just kind of doing a little bit more math in my head here. I have a 2x cubed plus 3x minus x minus 2. And hopefully you can see that each and every one of these is not opposite. They look like they're opposite, except you have this final value here that messes really everything up. Oops, that's supposed to be a negative. How did I mess? Oh, I forgot to write the squared. I was wondering, I'm like, that's supposed to be negative. So you can see how they're not all the opposite, nor is it the same. So this is neither even or odd. And typically, guys, when you're dealing with polynomials, not typically, but a little bit of tip, when you're dealing with polynomials, If it's going to be even, it's going to always have even powers. Not coefficients, but even powers. If it's odd, it's going to add odd powers for your exponents. And even powers can have a coefficient of 0, whereas odd powers cannot. Or not a coefficient, but a constant. Not constant of 0, just a regular constant. You can see how this one didn't change the value, right, when you had that constant. Therefore, I know it's not going to be even. And since there was even powers or odd powers and even powers, that's why another way to look at that is neither. But you notice here for D, E, and F are not polynomials, so we don't want to follow those rules. What we're going to need to do is, again, check it out. So we plug in J of negative x. So I get negative x squared minus 3 times negative x plus 2. Here I get an x squared plus 3x, oops, x squared plus 3x and plus 2. And again, you can see that it does not produce the opposite or the same as my original function. So again, this is neither. All right, the next one here, k of negative x. Therefore, we have a negative x all over a negative x squared minus a negative x. Whew, lots going on, right? So let's see, we get a negative x all over a x squared plus x. Now, sometimes this that gets a positive. I think I was supposed to write that as a, I wonder if I wanted that to be x squared. I don't remember what I was saying. All right. But anyways, remember when you have a negative, you can always take that negative and put it out in front. And if you put it out in front, you would be left with a positive x over a x squared plus x, which you guys can see is going to be not the opposite, nor does this produce the exact same of that function, so therefore this is neither. I think I wanted to change that function. I think I was thinking that to be an even, so I have to maybe change that. But either way, for this example, you can see that it's neither, or maybe, oh no, it's supposed to be odd. All right, I'll have to play around with the numbers then to make that odd, because it's supposed to be the opposite. That's positive, so that needs to be negative. Okay, all right, I'll work on that. Anyways, so next one, k of negative x, or yeah, k of negative x. It's going to give you a 5 over square root of 1 minus negative x squared. Well, negative x squared is a positive x squared, so you get 5 over square root of 1 minus x squared. And there you go, you can see that that one is even. Let's just play around with this. What would we want that to be? If we made that a squared, whatever, I'll play around with that later. But either way, basically that's what we wanted you guys to do, is plug in those values and go from there. And hopefully you guys learned a little bit about operations of functions, as well as how to identify the domain and the range. The last thing I ended up the lesson here with just asking some students to do a little reflection and, kind of talk about what they learned and what they didn't, what they had trouble with, understanding from the lesson. So hopefully you guys enjoyed that. And if you have any questions or anything about this lesson, feel free to comment below, and I'll be more than happy to assist you. Cheers.